All right. Hi, I'm Yanfei from Argonne National Lab. So I'm going to talk a little bit about how we support OFI and what are the latest advancements in the MPICH library in terms of using OFI features. So I'll start with a little bit about what MPICH is and basically why we want to use OFI in our library, and then we talk about the current support and some ongoing work. Okay. So in case you're not familiar, so MPICH is an MPI implementation that has been widely used. And in MPICH, we care about three things. The first is the compliance with MPI standard. So every time when the MPI forum roll out a new version of standard, we are trying to make sure that our library has a software release that supports the entire new standard features. And second thing we care a lot about is performance, and third one is the portability. So the entire MPICH project has been led by our group at Argonne National Lab and collaborator at UIUC. And at the same time, we also have many vendor collaborators who contributes feature and bug fixes to our code, and also use our code for their own product. So the current library has a stable release of 3.2. That was a little while ago, but that was back in 2015, I believe. And the latest release is actually a beta 2, which has just been rolled out this week. So the way that the MPICH library work is, instead of building a single library or a single product, we're trying to maintain and run what we call an MPICH ecosystem. So we have the MPICH library at the center. Basically, this is more like a reference implementation that have this full support of the standard and with optimized performance. And our vendor collaborators like Intel and IBM and Cray, they will take our code base and apply their specific optimizations for their network hardware or their software tool set and release them as their own product. So combine all these implementations, we basically all the MPICH and MPICH derived MPI implementations have run on 9 of top 10 supercomputers on the top 500 list. And above that, we also have a very close collaborations with the tools community that focus on how to better provide information to the debugger, profilers, and we also have a close collaboration with the higher level libraries such as PET-C and other tools that used in the scientific computing community. So for MPICH, we're having a big transition time from the existing CH3 device implementation to a more use OFI more in our implementation. So the main reason behind this transition is, if we look at some of our old implementation, like the CH3 device, what happens is back then we trying to basically implement all the communication features and support different network hardware by introducing different net mod. But the downside with the CH3 design was that all the communication is pretty much done in an active message context. So for example, if we have, essentially we just do a lot of internal protocol, and when we hit the OFI net mod, we just call it T receive and T send. The downside is, of course, it comes with a lot of overhead and pretty much not use all the high-level semantic that OFI is providing today. So we decided that we need completely overhaul this design and try to implement a new hardware for OFI. And with that in mind, basically with OFI, the major benefit, one is the high-level abstraction, semantics that is more close related to what MPI needed, and basically we're able to provide a thin layer of abstraction that allow the MPI semantics to directly work on this. And secondly is the hardware support, of course. So in the MPICH 3.3 series, what we introduce is a CH4 device. It's a new abstract device layer for using OFI and also other network libraries. So the idea is we're trying to replace CH3 with a much lightweight design. So there's two main objectives in the CH4 design. One is we're trying to achieve a low instruction count communication. So the reason is that basically all the new network libraries such as OFI and UCX, they all support a high-level network APIs. Instead of just doing send and receive, they have support for tag matching, well, depending on hardware. So and RMA. So if we look at what MPICH used in CH3 is basically adding overhead and without using these features. So in CH4, what we're trying to do is we're trying to remove these heavily designed protocol to just some fallback. And for the network that is capable of doing like hardware tag matching, hardware support of RMA, we're just passing the function call to the OFI layer or UCX function calls. And apart from the low overhead communication, the second thing that we're trying to do is trying to improve the communication performance for multi-threaded MPI, especially for the MPI-threaded multiple model. I'll talk about that later. So here is a kind of a highly abstracted overview about CH4. So basically, so you see if you look at the MPI layer, oops. Okay. So if you look at the MPI layer, this is what the user will be calling, the user application will be calling all the MPI functions. And as CH4, we basically only introduce a very thin layer of abstraction, trying to make sure that the user call translated to the correct network APIs. So if your hardware is capable of doing hardware tag matching, for example, or RMA, basically this thin layer just a very simple function call. The way we're doing here is basically remove all the function pointer that we use in the CH3 design because we found those are pretty expensive, and we're trying to inline as many as possible for all the functions in the performance critical path. For example, ISEN, IReceive, and put/get. And apart from that, there's a set of what we call CH4back functionality that is optional if your hardware doesn't support certain features. So we have the entire active message-based communication model in the fallback, and we also have the collective algorithm in there. So if your hardware doesn't have a hardware accelerated collective, you can still do collective with the existing algorithms. So the benefit with this is for really fast hardware, we have a really low overhead. The measurement we got is only for MPI send is around 40 instructions. But at the same time, if you're trying to support new hardware, for example, in OFI, if you want to add a new provider, what MPI requires to work on this new provider is that you provide the basic message interface. So with then the MPI library can just do active message for all the communication. So one experience we recently have is that we were helping out some collaborators from different institutions because they have a very new hardware they're working on is very experimental, and they're trying to write a provider. So our team and their team, we have about 5, 6 people working on this for like, we spent 3 weeks writing this new provider, and just a very basic the FI message interface, and then now we can run MPI on this new hardware. Although the performance is not great because it's all active message, but then again, if this is, I think it's for us, it's easier to try on new hardware, and for the hardware developers or the network provider developers, it's easier to see how their work has broader impact if using MPI. So if we go to the extreme, we actually can also can inline the entire OFI library as part of the MPI library. So there's completely eliminating the function call between these different abstraction layers. So that is the current status of how MPI is supported in how OFI is supported in the MPICH library, and we have a paper in last ESC detailing about what kind of optimization and what kind of inlining and special building techniques that we can use to further reduce the overhead. But now let's look at the second thing we are trying to talk about today is we are trying to improve the performance with multi-threaded MPI, especially with the MPI+THREAD multiple model. So in this model, basically, in each process, you can have multiple threads that issuing MPI calls. But the current status of MPICH library is the performance is really bad if you compare it to the single-threaded version. The main problem is with this locking mechanism. So right now, whenever the user application calls an MPI function, we have to acquire a lock in order to go into the actual critical section that does the communication, issuing the message, and or pulling the progress. What happens if you look at this MPI ISON implementation? This is very simplified, but what the function does is try to get a lock and call the device function to send message. But the problem is this lock is basically all the threads have to contend for this lock. So for non-blocking operation like ISEND, you still might block at the place where you're trying to acquire a lock. And to make things worse, this ISEND function would also run into contention with MPI wait. So if you have one thread waiting for the completion of some operations while other threads trying to issue a message, unfortunately, that issue will be blocked until that wait is finished. So at the end of the day, these results in very poor performance with multi-threaded communication. So with that in mind, what we're trying to do in CH4 right now is we introduce this what we call work queue model. So if we think back, the problem with the current locking scheme is that a thread comes in and trying to get a lock. It won't get the lock. While you may, then it might block on that. And one intuitive solution to that is to incorporate a try-lock mechanism. So you try to get a lock. If it doesn't come, you can just go back and wait for a while and try to get a lock again. But then you're just spending time just waiting on this lock, just instead of blocking on it. So it doesn't solve the problem. So what we're trying to do is we're trying to introduce a queue where if you get locked, you're just issuing your message, no problem. But when you try to get a lock and cannot get one, and instead of just go back and wait, you just create a work descriptor, what we call it, and put it into the queue. And for the thread that actually has the lock, what it should do is first it look into the queue and see if there's any pending work that has been included by a different thread, and trying to dequeue and issuing all that message in the queue first, and then issuing his own message. So in that case, basically we're decoupling the issuing process and the locking in some sense. So the basic benefit is that the thread won't have to waste any time on just trying to get a lock instead of doing actual message or doing any useful work. The code might be too small here. So basically here is an example. Like I mentioned, for non-blocking calls like MPI could run into conflict, contention with MPI wait because they all have to get a lock. And using the work queue model basically also avoids these cases where because whoever has the lock to the critical section will try to keep issuing the work that is in the work queue. So in that sense, basically for the entire program, will be spend less time just waiting for unlocks. So with the work queue model in mind, we basically trying to introduce multiple queues. So for example, let's say we have different communicators and these communicators might be shared by a different thread or not. And in the MPI layer, what we can do is we can have different queues for each of them. And when they're trying to enqueue work that goes to the different queues, and we can. The benefit of this is basically you are also reducing the contention between the queues, right? Because if you don't, while the thread that doesn't get the mutex lock is enqueuing data into the work queue, but the queue itself needs some sort of synchronization. Currently, the current implementation we use lock-free queue, but there's certainly overhead associated with that, and with multiple queues, we can basically kind of reduce that contention in that region. And depending on the need of the application, these can be per rank or per communicator, and it can also be associated with different operations. Like you can have dedicated queue for our RMA operation, while there's separate queue for point-to-point communication. But if you look at all these queues, so after all the work has been put into these work queues, they all need to be issued on this what we call a virtual network interface, a VNI. So what VNI does is basically an abstraction of the network resource that MPI can use for communication. For OFI, this could easily be the endpoint or the context in a scalable endpoint. And it also can be the network context in IB variable or the worker, a UCX worker. So the next thing we're trying to see is how now we solve the contention at the MPI level, and the next question is how we can improve the utility of the hardware resource, right? Because if you have a multi-threaded application, you may only have one process per node, while you have many threads in there. But with the previous single VNI implementation, the problem is you are not using all the hardware contexts that you can to issuing your message, which leaves most of the resource underutilized. So what we have here is you can create multiple VNIs and bind the queues to different VNIs. So with that, basically we can, for example, with OFI, we can have a dedicated VNI for RMA operations and a different VNI for point-to-point, and attach the queues to these VNIs respectively. But note that it is not a one-to-one mapping between the queue to the VNIs, because you can have many queues and they can share VNI or not, depending on how you want to optimize your application. or the communication. And basically what we're trying to do is when you can provide this information as a hint when you create communicators, and within the library we'll tie the queues to the VNIs correctly, depending on the hint. So we have some preliminary results of using this. So this is using actually it's not using OFI. This is using a Mellanox QDR fabric. So you see the dark red line here is the multi-thread MPI performance with no work queue implementation, no optimization at all. You see that, and the orange one is the one with the work queue, and the performance improvement is roughly around four times. And this is still an ongoing work. This is some preliminary result, and we're trying to get more and test on different hardwares in the next few weeks. So at last, I would like to talk about what are our plan for the future. So we have just released 3.3 beta. So the entire the major improvement in the entire 3.3 series is the introduction of CH4 device. So we already have some. It's out in the wild for a while. So I think our vendor collaborators has already trying on that and have some experience. And next, we basically have another beta release in the next month, I think, and we'll have the initial implementation of the work queue, and we'll also add the multi-VNI support in the GA release for the MPICH 3.3 that is due in the summer of this year. And with that, that's all I want to talk about for the OFI support in MPICH, and I would happy to take any questions.
Hi, good presentation. So my question is related to load balancing. How do you balance load between a process having multiple threads versus multiple processes? Because it looks like the queues are within a process. So how do you know the global view of across processes?
You mean like multiple processes on one node with multi-thread?
Yes, within a node, because like the scalable endpoints provides you some kind of interface, but how do you know like the first process is not consuming most of the resources, hardware resources, versus spreading it across processes?
Okay, so so the load balancing is pretty much done by assigning different hardware contexts to different processes. So you can either do this symmetrically or asymmetrically depending on your need, right? This is something that is configurable at any time. So for example, if you know one of the process have more work to do, you can assign a little bit more hardware context to it if that's what you need. But basically by default, we're trying to assign the same amount of number of hardware contexts to each process.
I have kind of a related question. It's around, when you allocate your virtual interfaces, and then you have a work queue or multiple work queues that are bound to that, and then they issue the requests out that goes down to a hardware context. Do you have ways to make sure that, for example, the threads that are issuing the actual sends to the virtual down to the hardware are on the same CPU socket, for example, is where the NIC is located? In some platforms, for example, if you're going cross-socket, like if one thread or one process issues a request that has to go to a NIC that's on a remote socket, there can be a performance penalty.
That's a good question. I think that's in the current implementation we haven't gone that far yet, but we'll definitely look into the optimization for that specific case. But I guess it's also kind of depending on how how the progress was made when we deplete the queue. I think one ideal case is if we have only one process and all the threads are running on different cores, and if we bind them, we can sort of having one thread just doing all the heavy lifting. Although would that be beneficial in that particular case is we have to do more experiment with that, and but we're definitely looking to optimize for that case. Any more questions? Thank you.